In 1850, a British archaeologist digging through the ruins of an Assyrian palace pulled a small disk of rock crystal out of the dirt. It was 38 millimeters across, ground to a precise convex curvature, with a focal length of approximately 12 centimeters. It sat in the British Museum for 150 years, labeled as a decorative ornament. When optical engineers finally measured it in detail, they confirmed it was a working lens. The Assyrians made it nearly 3,000 years ago, roughly 1,400 years before the earliest documented European optics. Cuneiform tablets from the same palace describe astronomical observations that would have been impossible to record without magnification. The artifact is known as the Nimrud Lens. It measures 38 millimeters in diameter, 23 millimeters in thickness at its center, and weighs approximately 75 grams. It is ground from a single piece of natural rock crystal, a transparent variety of quartz with a Mohs hardness of 7. The convex face has a measured focal length of approximately 12 centimeters. The opposite face is roughly flat. The surface finish on the convex side is sufficiently uniform to produce a clear, magnified image of objects placed at the focal distance. The lens was recovered from the Northwest Palace at Nimrud, a Neo-Assyrian royal complex located on the east bank of the Tigris River in what is now northern Iraq, roughly 30 kilometers southeast of Mosul. The palace was constructed under Ashurnasirpal II between 879 and 869 BC and remained in active royal use until the city's destruction in 612 BC during the fall of the Neo-Assyrian Empire. The lens was found in a context dated to the 8th or 7th century BC, placing its manufacture roughly 2,750 years before the present. The conventional history of optics places the earliest verified magnifying lenses in 13th century Italy, associated with the development of reading glasses around 1280 AD in the workshops of Pisa or Venice. The earliest documented use of curved lenses for astronomical observation is Galileo's telescope in 1609. The Nimrud lens predates the Italian reading glass tradition by 1,950 years and Galileo's astronomical optics by 2,400 years. By every conventional marker of pre-classical technology, none of the equipment we associate with optical-grade lens manufacturing existed in the Assyrian toolkit. No precision grinding wheels, no calibrated abrasive systems, no curvature measurement instruments, no surviving documentation of optical theory, no recorded vocabulary for focal length or magnification. The Assyrian written record, extensive in administrative and astronomical content, contains no description of how the lens was made or what it was used for. The earliest known ground-curved lens on Earth was sitting in a museum drawer for a century and a half before anyone measured it. The first serious modern investigation of the Nimrud lens as an optical object rather than a decorative one was conducted by British scholar Sir David Brewster, the physicist who had developed the kaleidoscope and conducted foundational work on the polarization of light. Brewster examined the lens shortly after its arrival in London and published a paper in 1852, stating directly that the artifact was a magnifying lens with deliberate optical properties. His conclusion was based on direct measurement of the curvature and focal behavior. The British Museum catalogued the lens as a decorative inlay anyway. Brewster's analysis sat in the literature unaddressed for nearly 150 years. The investigation was reopened by Italian physicist Giovanni Pettinato of the University of Rome, who in 1999 examined the lens and a series of cuneiform astronomical tablets from the same period. Pettinato's central claim was that the lens functioned as a working magnifier capable of supporting astronomical observation, and that specific Assyrian astronomical records contained details about Saturn that he argued could only have been recorded by an observer using optical aid. The most cited example is a tablet describing Saturn surrounded by what Pettinato translated as a ring of serpents, which he interpreted as a recognizable pre-telescopic observation of Saturn's ring system. The interpretation was contested immediately. Other Assyriologists argued the tablet text was metaphorical rather than observational, and that Pettinato had overread the optical implications. The dispute remains unresolved in the scholarly literature. What is not in dispute is the optical character of the lens itself. In 2001, optical engineer J. Enoch of the University of California, Berkeley, conducted detailed measurements of the curvature, surface finish, and focal properties of the Nimrud Lens and a series of comparable rock crystal artifacts from Egypt and Crete. Enoch's published analysis concluded that the Nimrud Lens was deliberately ground to produce a specific focal length, that the curvature was not consistent with natural mineral cleavage or accidental polishing, and that the artifact represented intentional optical manufacturing. The central engineering question that emerged from Enoch's work is straightforward. How did 7th century BC Assyrian craftsmen grind rock crystal to a controlled convex curvature with a usable focal length, using only the abrasive technology documented in their period? That question has not been answered. The fringe theories around the Nimrud Lens are quieter than around Baalbek or the pyramids, but they exist. The lens has been folded into ancient astronaut frameworks as evidence that extraterrestrial visitors provided the Assyrians with optical technology, with the focal precision presented as proof that no human civilization of the period could have ground rock crystal to working tolerances unaided. A more developed alternative claim, advanced in popular alternative history media, places the lens within a lost technological civilization that predated the Assyrians and was destroyed in some prehistoric catastrophe. In this framework, the Assyrians inherited the lens as a recovered artifact rather than manufacturing it themselves, and similar lenses found in Egypt, Crete, and elsewhere are scattered fragments of the same vanished optical tradition. The argument has surface appeal because the related artifacts genuinely do exist, and the manufacturing process is genuinely poorly understood. The more interesting fringe argument concerns Saturn specifically. Pettinato's interpretation of the cuneiform tablet describing Saturn surrounded by serpents has been adopted enthusiastically by ancient mystery channels as proof that the Assyrians had functional telescopes, with the lens presented as one optical element of a larger lost instrument. The leap from a single magnifying lens to a working refracting telescope requires multiple matched optical elements and a tube assembly, none of which has been recovered from any Assyrian context. What unites these theories is the assumption that an Iron Age civilization could not have ground a working lens through patient empirical experimentation, therefore the lens must have been inherited or gifted. This assumption is doing more work than the evidence supports. The Assyrians were demonstrably sophisticated craftsmen working in cylinder seals, intricate metalwork, and precision stone carving. The cognitive and manual capacity to grind a curved surface from rock crystal sits within their documented capability, even if the specific procedure is not preserved in their texts. The genuine mystery is not whether ancient humans could have made the lens. They clearly did. The mystery is what they made it for, why the optical tradition appears to have stopped developing rather than expanding, and whether the lens represents an isolated experiment or a routine product of a workshop tradition that simply left no other surviving examples. The supernatural explanations distract from the more interesting human question. The optical analysis conducted by J. Enoch and his colleagues at Berkeley provides the densest body of physical evidence on the Nimrud Lens. The measurements are direct, repeatable, and have not been seriously contested since publication. The convex surface of the lens has a measured radius of curvature of approximately 116 millimeters. The focal length calculated from this curvature, accounting for the refractive index of natural rock crystal at 1.544, falls between 110 and 120 millimeters. The focal length is consistent across multiple measurement attempts, indicating that the curvature is uniform across the optical surface rather than approximated. A naturally polished or accidentally smoothed crystal would produce inconsistent focal behavior across its surface. The Nimrud lens does not. The surface finish is the more telling evidence. Microscopic examination reveals fine, concentric grinding marks consistent with rotational abrasive contact. The marks are uniform in spacing and depth across the convex face, suggesting the lens was ground against a rotating bearing surface rather than hand-polished with random motion. This points to the use of a primitive, lathe-like apparatus, possibly a bow-driven rotational fixture of the kind documented in Egyptian bead-making and stone vessel production from the 3rd millennium BC onward. The flat reverse face shows a different finish pattern, with linear grinding marks consistent with flatbed abrasion against a stone slab using sand or emery as the cutting medium. The two surfaces were finished using different procedures, indicating deliberate intent to produce specific optical geometry rather than uniform polishing of an ornamental object. The peripheral edge of the lens is roughly worked and shows no evidence of mounting hardware, suggesting the lens was held by hand or set into a soft material like leather or wood that has not survived. There are no inscriptions, no decorative engraving, and no evidence of pigment. The artifact is unornamented. This is consistent with a tool, not a piece of jewelry. Comparable rock crystal artifacts recovered from Egyptian sites, including a well-documented example from the tomb of Sabu at Saqqara dated to the First Dynasty, show similar manufacturing characteristics. Cretan examples from Knossos, dated to the late Minoan period, follow the same pattern of controlled convex grinding with differential surface treatment. Physical evidence rules out accidental polishing. The lens was engineered. The most thorough recent optical analysis of the Nimrud lens was conducted by J. Enoch and Vasudevan Lakshminarayanan and published in 2002 in the Hindsight Journal of Optometry History. Their work used calibrated optical bench equipment to measure the actual imaging behavior of the lens rather than calculating its theoretical performance from curvature alone. The distinction matters. A lens can have a measurable focal length without producing a usable image. The Nimrud lens does both. The team mounted the artifact in an optical fixture and tested its magnification capability against standard targets at varying distances. The lens produces a clearly resolved magnified image at distances between 8 centimeters and 14 centimeters from the convex surface, with optimal magnification at approximately 12 centimeters. The magnification factor is roughly 2 times, sufficient to enlarge small text or fine engraving to readable size. The image quality shows spherical aberration and minor distortion at the edges, consistent with a single uncorrected convex element, but the central field is clear enough for practical use. Enoch and Lakshminarayanan also conducted comparative analysis across the broader corpus of pre-classical ground crystal artifacts. Their study examined 23 separate objects from Egyptian, Mesopotamian, Minoan, and Phoenician contexts, dating between the 4th millennium BC and the 6th century BC. Of these, 17 showed deliberate convex grinding consistent with optical function. The artifacts cluster into 2 functional categories: simple magnifiers in the 1.5 times to 3 times range, and what the authors describe as low-power burning lenses capable of focusing sunlight to ignition temperatures. This matters enormously. The Nimrud lens is not an isolated anomaly. It is part of a broader pre-classical optical tradition that spans multiple civilizations and at least 2,000 years of continuous activity, with 17 surviving working examples from across the Eastern Mediterranean and Near East. Cuneiform astronomical record from the same period contains observations of stellar positions, planetary motion, and lunar features recorded with positional accuracy that has been argued by some Assyriologists to require optical aid. The argument is contested. The lenses themselves are not. History of optics, as currently written, places the invention of the magnifying lens in 13th century Italy. The physical evidence places the working magnifier in 7th century BC Iraq, with antecedents reaching back another 2,000 years. The optical tradition behind the Nimrud lens does not appear to have transmitted forward in any continuous lineage. This is the more troubling finding once the corpus of pre-classical lenses is examined as a whole. The 17 working optical artifacts identified by Enoch and Lakshmanarayanan span roughly 2,000 years of intermittent production across Egypt, Mesopotamia, Crete, and the Levantine coast. After the destruction of the Neo-Assyrian Empire in 612 BC and the subsequent collapse of the late Bronze Age workshop traditions in the broader region, the optical record goes effectively dark. Greek and Roman sources mention burning glasses and crude magnifiers, but no surviving classical artifact matches the manufacturing precision of the Nimrud lens or its Egyptian and Minoan parallels. The technology appears to have existed, been practiced, and then been forgotten, with the next confirmed working magnifying lenses appearing in the 13th century Italian reading glass workshops nearly 1,900 years later. The medieval rediscovery of optics is independently documented. Roger Bacon's Opus Majus, completed around 1267, describes the magnifying properties of curved glass surfaces. Italian glassworkers in Pisa and Venice developed reading glasses by 1280. The German astronomer Johannes Kepler systematized optical theory in 1604, and Galileo turned the resulting telescope toward Jupiter in 1610. The lineage from medieval Italian glasswork forward is continuous and well attested. The lineage backward into the pre-classical period is missing. Whatever workshop tradition produced the Nimrud lens did not transmit its methodology to the Greeks, the Romans, or the medieval Europeans. The technique was lost. The collapsed distance moment here is sharper than at most ancient sites. Every pair of corrective glasses worn today, every camera lens, every microscope objective, every telescope mirror descends from optical principles that were rediscovered in the 13th century. Those same principles were already in working application 2,000 years earlier, in workshops whose names are not recorded and whose methods were never written down. The technology is not new. The continuous documented version is new. The capability is older. Whoever ground the Nimrud lens understood, at minimum through patient empirical observation, that a curved transparent surface bends light in predictable ways. They acted on that understanding to make a tool. The tool worked. The understanding did not survive them. The Egyptian bead-making industry of the pre-dynastic and early dynastic periods, operating from roughly 4000 BC onward, was producing precision-drilled stone beads with bore tolerances under 0.1 millimeters using bow-driven rotary drills with sand or emery as the cutting medium. The same rotational technology, applied to grinding rather than drilling, produces exactly the kind of uniform concentric surface marks observed on the Nimrud lens. The capability was already present in the regional workshop tradition more than 2,000 years before the lens was made. Mesopotamian cylinder seal carvers of the 3rd and 2nd millennium BC routinely produced miniaturized intaglio designs at scales requiring acute visual focus. Some of the finest cylinder seals from the Akkadian and Old Babylonian periods contain figural detail measuring under 1 millimeter per element, executed with sufficient precision that modern museum conservators have argued the carvers must have used some form of magnification to produce the work. The presence of working magnifiers in the same broader cultural region during this period is consistent with that argument. Greek mathematician and engineer Archimedes, working in the 3rd century BC, conducted experimental work with curved mirrors and is credited in later sources with theoretical descriptions of focal behavior, though no surviving Archimedean text preserves the optical analysis directly. The capability to reason about curved optical surfaces was present in the Hellenistic intellectual tradition that absorbed and extended Mesopotamian and Egyptian craft knowledge. The replication question is straightforward. Modern lapidary craftsmen using only abrasive sand, water, and a bow-driven rotary fixture have successfully reproduced the surface curvature and finish of the Nimrud Lens in experimental archaeology trials. The process is slow, requiring sustained grinding over multiple days for a single lens of comparable size, but it is achievable. The methodology is not exotic, it is patient. The same problem-solving mind that designed cylinder seals at sub-millimeter resolution, that drilled stone beads to optical-grade bore tolerances, that built the astronomical observation traditions recorded in cuneiform tablets, was capable of grinding a curved transparent surface to a controlled focal length. The capability was present. The execution was deliberate. The artifact survives as direct physical proof. The Nimrud Lens is not an anomaly that requires explanation from outside the human record. It is a working tool produced by a workshop tradition operating at the edge of what coordinated craft knowledge could achieve at the time. The conventional history of optics begins in 13th century Italy. The Nimrud Lens does not fit that history. It sits in the British Museum as physical evidence that the timeline is wrong, or at minimum that the timeline describes only the documented continuous tradition and not the full record of human optical capability. The artifact is real, the curvature is measured, the focal length is repeatable, and the manufacturing marks indicate deliberate engineering. None of this is contested anymore. What remains contested is what it means. The optical analysis did not reveal advanced lost technology. It revealed a working magnifier, ground by hand from a single piece of rock crystal, capable of about 2 times magnification, sufficient to support reading fine inscription or examining small craftwork. The lens is not a telescope. It is not a microscope. It is a hand magnifier of the kind a watchmaker or jeweler might still use today. The ordinariness of the object is the most important thing about it. Someone in 7th century BC Assyria needed to see something small more clearly and ground a tool to do it. What still cannot be answered is the scope of the tradition that produced it. The 17 working optical artifacts identified across Egyptian, Mesopotamian, Minoan, and Phoenician contexts are surviving examples. The original production volumes are unknown. The workshops that made them are unidentified. The texts that would have described their use, if such texts existed, have not been recovered. The Cuneiform astronomical record contains observations that some scholars argue required optical aid, but the connection between the lenses and the observations remains an inference rather than a documented link. If a working optical tradition operated for 2,000 years across the Eastern Mediterranean and then vanished from the record without forward transmission, the question of what other technical capabilities followed the same trajectory becomes harder to dismiss. The Nimrud Lens is not an isolated mystery. It is a single durable survivor from a broader pattern of pre-classical technical knowledge that left fewer traces than the monumental architecture of the same period, and consequently has been studied far less. The first magnifying lens on Earth is older than Rome, older than Athens, older than the Hebrew Bible. It is sitting in a glass case in London.